Hi, and welcome back. So let's continue with our journey on limits. Alright, so we saw in the previous lesson that a limit is a value that a function approaches as x approaches a certain number c from either side. Okay, an example that we used was this. Right? Okay, so we saw that as x approaches 3, f of x approaches 10. Right, so 10. There we go. Alright, and this is the notation that we use right here. Okay, so let's do another problem that's going to be easier. Remember that with this problem, how we solved it was we drew a table. Let me find that. Right, here we go. Remember this? Right, we drew a table, and we saw that f of x approaches 10 from both sides. And we also drew a graph, which confirmed our findings. Okay, so let's do a new problem. It's going to be very easy. So my question is, our function is going to be f of x is equal to x cubed plus 1, and my question is limit of f of x as x approaches -2. Okay, so that's my question. So you know what, let's draw a graph. If you remember, this is basically x cubed shifted up 1. Sorry. Okay, so it's gonna look something like this. Not perfect, but close enough. There we go. Right, so notice that in this problem, we do have a value for f of x at x equals -2. It does exist. Right? F of -2 does exist, and that equals -7. But does it matter though? Does it matter to this question? No, it doesn't. Right? Because with the limit, we only care about what happens around x equals -2. We don't care about what happens at x equals -2. But you know what? Sometimes this value can be useful to finding the limit. Okay, so if we do this and we evaluate this graphically, we see that as x approaches -2, f of x approaches 7. And that's our answer. And take a look. Both of these are the same. And do we expect them to be the same? Yes. Yeah, we do. And this is a trait for all polynomial equations. Right? So a polynomial equation is basically terms added up together or subtracted. And each term has a coefficient times x raised to a certain power. Okay, so this is a polynomial. And with all polynomials, the limit at a certain point equals the value of the function at that point. Right, so the value of the function at x equals 2 equals the limit of f of x as x approaches -2. And does that make sense? Absolutely. Because we wouldn't expect the function to equal something that the limit didn't for polynomial equations. But you know what? Let me give you an example of an occasion where this does not hold true. Well, this is going to be silly, but nope. Let me write this on the page. It's going to be silly, but take a look. What if I defined this function? We can use we're going to use this notation. Okay, a split function more or less. You know what? Let me create this. this function here. Alright, so what this function says is that, what this function says is that if x is not equal to -2, f of x is equal to x cubed plus 1. But if x is equal to -2, f of x is equal to 2. And if we draw this, it's actually going to be the same graph, except, you know what? Let's just use this because it's so much easier. There's going to be a hole here. So instead of a dot, it's going to be a hole. Right? I don't have to white it, but I would white out the center of this hole. And a dot would be here. Do you see? So we basically moved this thing up here. What happens in this case? Okay. What happens in this case? In this case, actually, no longer is equals f of 2 no longer equals -7, but it equals what? -2. Because we changed the function here. And let me ask you a question. What about the limit? The limit of f of x as x approaches -2 is equal to what? -2? No. Right? Remember, with limits, we don't care what happens at x equals 2. We only care about what happens around it. So let's use our fingers, and we see that as we approach x equals 2, boop, these two fingers are still reaching -7. In this case, we saw that the value at x equals 2 is actually different than the limit of f of x as x approaches -2. The function and the limit do not coincide. Right? So we have to be very careful. In special cases, the limit and the function are equal to each other. And I told you that this is true for all polynomial equations. But if we have a special function, we have to take special care to, if we have a special function, we have to take, we have to be careful not to jump to any conclusions, right? Because we saw here that the function does not equal the limit at x equals 2. Okay, so let's do some more examples. Same concept. Okay, so what I'm just going to give you a graph instead of telling you a function. Okay, so it's going to look something like this. Okay. Okay, so this is a wiggly function that has a hole at x equals 2. Sorry, it doesn't have a hole here, but it has, at here, you see this sort of a jump, a discontinuity, right? So at x equals 2, this function is equal to 5. Okay, so this is f of x. Okay, so my question to you is, limit of f of x as x approaches 4. Is it 5? No. It's equal to 2. Do you see that? This question is 5. This question is 5. This question is 2. Okay, so that's a limit for you. Let's do one more. Okay, notice here that, you know what? Let me play around with this. What happens if I move this dot over here? Does this change? No, the limit doesn't change. This thing actually does change. The value of the function at x equals 4 changes if I move this value around, this dot around. But the limit doesn't change. Right? So if I took out this thing and put it here, this limit is still true. This changes though. If I move it here, same story, limit doesn't change. Limit never changes if I play around with this function at x equals 4. I can move this dot however I want. You know what? I can even take out all the dots such that it doesn't exist. Such that this function doesn't exist at x equals 4. So now, this is undefined, but this limit still exists. So you know what? I could actually just black out this entire thing. If someone gave me this graph here, there you go, gave me this graph and asked me for this limit, I can find out the answer because I don't need to know what happens at x equals 4. I only need to know what happens around it. And using this graph, I see that around it, as x approaches 4, we see that this graph approaches 2. Okay, so hopefully I repeated this so many times, but hopefully you understand it now. With limits, we only care about what happens around it. And so we have time for one more example, quick one. Okay, so let me give you another split function here. Okay. Here we go. So the function here reads, if x is greater than 2, then f of x is equal to 9. If x is smaller than 2, f of x is equal to 5x minus 1. And if f of x is equal to, and if x is equal to 2, f of x is equal to 5. Okay, so you know what? Let's draw this function out. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2. Okay, so we see that if x is greater than 2, f of x is always equal to 9. At x equals 2, 1, 2, 3, 4, 5. At x equals 2, f of x is equal to 5, so let me draw a dot there. Okay, and if x is smaller than 2, f of x is equal to 5x minus 1. So how does this work? Let's see, minus 1. Over 1. There you go. And that 2 equal 9. Okay, so let's take a look at this. Here already again, let's play around with left-hand limits and right-hand limits. So the left-hand limit of f of x as x approaches 2 from the left negative sign is equal to what? 9. Right? Let's do a right-hand limit. Okay, so take a look at this. If we come in from the right with numbers that are greater than 2, equals 9, 9. And then what? The left limit equals the right hand limit. These two are equal, check. Therefore, we do have a limit, and this limit is equal to 9. Okay? So, that's the limit. Remember that the left hand limit has to equal the right hand limit for this limit to exist. And we couldn't care less what happens at x equals 2. We don't care. Here it's equal to 5. Here can move this down here, can move it here. We don't really care. Okay? So always check to see that your left hand limit equals the right hand limit, and if they do equal, the limit does exist. If these two numbers are not equal, the limit does not exist. And we'll take a look at limits that do not exist in the next lesson. See you later.